Hello everyone, welcome back again. We'll continue our lecture on alcohols, ethers, and epoxides. I hope you have a general understanding of alcohols, ethers, epoxides in their physical, chemical properties and naming of alcohols, ethers, and epoxides. But now we will move on to how to make these alcohols and ethers. Basically, in this lecture, we will see how to synthesize an alcohol or an ether based on what we know before. So these are the reactions we have already known before in terms of mechanism. So in synthesizing an alcohol, for example, if you have a primary alkyl halide, which we have already discussed in previous chapters, alkyl halides can be primary, secondary, or tertiary. But for this particular lecture, we'll be just focusing on a primary alkyl halide and a reaction with a strong nucleophile, which is a hydroxide ion. So it is a primary alkyl halide, remember, one property of this, how to synthesize an alcohol. And you use the OH group, the OH minus. It can be in the form of sodium hydroxide, potassium hydroxide, but it's a very strong nucleophile, if you remember. Now, by an SN2 reaction, the OH would substitute the halide, that means the leaving group. So this OH minus attacks this carbon. It is SN2, that means the attack and the leaving group leaves at the same time. So this is a primary alkyl halide. So when this base, strong nucleophile, acts on this carbon, this leaves, that means as SN2. So it's primary alkyl halide, and the type of mechanism we are discussing here to make the alcohol by substitution of the alkyl halide is an SN2 reaction. So we would get our alkyl group CH2OH. So if you just see, this is an alcohol that's formed. Of course, you would have a leaving group that is X minus. Okay, so that's how you synthesize an alcohol. An alcohol can be synthesized from a primary alkyl halide. Remember now, and generally you have to remember, a primary alkyl halide, when it's treated with a sodium hydroxide or potassium hydroxide, a very strong nucleophile, it can undergo an SN2 substitution reaction. That's an alcohol. And if you were also, in the same analogy, if you were to make an ether, because an ether is, this H is, rather than being H, it is an R, it's an alkoxide. Now you don't use hydroxide to make an ether, you use an alkoxide, that's a strong nucleophile generated. It could be from sodium methoxide, sodium ethoxide, an alkoxide basically, and attacks this carbon in the same way. You would form R CH2OR. So that's an ether group, because you have an alkyl of this and another alkyl here. So that's an ether. So this is ether synthesis. This is alcohol synthesis. So for alcohol, you use a hydroxide nucleophile, and for an ether, you use an alkoxide. So basically, you just look at a structure. For example, if I didn't show you this, if I give you this and ask you how do you synthesize, you just cut it right here and see, okay, I will have an alkyl halide here, X, and an alkoxide like this. So that's the retro synthesis. This is a general scheme, and I will give you some specific compounds. For example, if you have this ethyl bromide, which is a primary alkyl bromide. If you treat it with a hydroxide, the hydroxide can come from sodium hydroxide or potassium hydroxide, ammonium hydroxide, and so on. So the hydroxide is a very strong nucleophile. So what you would get would be CH3, CH2, OH. So you have synthesized an alcohol by substituting the bromo-alkyl halide with an hydroxide. But if you were to make an ether, which is a little different than the alcohol, you use alkoxide. So for example, treatment of methoxide with this propyl chloride is an alkyl halide, still it's a primary one. Remember, the focus is these are primary. It is important to have a primary one because the reaction is SN2 reaction is much faster with SN2 type mechanism would be in a primary. So this product would be an ether or so CH3. So this group came in as a nucleophile. This is substituted, which has an X, which is this. And if you just look at this, this is also an ether formation. So ether can be formed CH3, CH2, O, CH2, CH3. So this alkoxide came in as a nucleophile, substituted on this bromine. So these are to be substituted. So for whether an alcohol or an ether can be synthesized from primary alkyl halide. This is a general concept you need to remember. If somebody asks you how you'd synthesize an alcohol, you'd say, okay, if I have a primary alkyl halide, and if I treat it with sodium hydroxide or potassium hydroxide, I can make a primary alcohol. So the alcohol is also a primary alcohol here. Here you are synthesizing an ether, so the ether needs an alkoxide nucleophile, so you have those ethers. So this is, in general, this alcohol is called ethanol. Remember, ethanol can be synthesized or also you can find biologically from fermentation ethanol. You know that this is the alcohol that's found in drinks. So that ethanol is synthesized from primary alkyl halide and a hydroxide. This is a propyl methyl ether. So it's a methyl propyl ether. This is a diethyl ether. This is called diethyl ether. This is symmetrical ether because they are the same in both sides of the oxygen. But this is unsymmetrical ether. So one thing I want to emphasize this would be this ether formation was discovered by a scientist named Williamson. So ether synthesis actually has it's a named reaction. Named reaction means that you have a name associated with it. So if somebody show a mechanism for Williamson ether synthesis, they meant that a primary alkyl halide reacting with alkoxide. So this named reaction, these are all named reaction after Williamson. So if somebody just prompts you by saying, we are doing Williamson ether synthesis, it means that you are reacting an alkyl halide, a primary one, with an alkoxide. So these reactions are actually named reactions. They are called Williamson ether synthesis. So in this course, I'm just introducing the first named reaction after Williamson. It's Williamson ether synthesis. Actually, ethers are synthesized by Williamson ether synthesis mechanism. That means You just take any primary alkyl halide, react it with the corresponding whatever you want the ether to look like with alkoxide, then you synthesize an ether. So this is a named reaction actually for the ether. It is called Williamson Ether Synthesis. So from now on, you need to remember what Williamson Ether Synthesis is. A Williamson Ether Synthesis is a reaction to make an ether from a primary alkyl halide and reacting it with a proper or appropriate alkoxide. So we'll continue more on synthesis. Okay, let's go a little deeper in the Williamson Ether Synthesis. So as I told you, Williamson Ether Synthesis is a very good way or good reaction to make ethers. But you have to also remember there are some judgments we have to make when we synthesize an ether. For example, you have this ether, which is what we have here, is the same ether, but it could be made by choosing an alkyl halide and also an alkoxide. So you have two possibilities here. You could use the alkoxide part, which is the green shaded area, could be act as an alkoxide, which is this, and the metal group, a metal which is alkyl halide, would have metal X. This is one possibility, right? So if you have this, you could make this when you break it down. Here, what about if I make the alkoxide this side, meaning that the nucleophile, which is in the green, and I have an X on that, which is alkyl halide, still it could potentially make the ether. But there are some practical considerations. That's why I'm bringing this very important concept here. Between these two reactions, one is much more favored or much more practical than the other. So in this case, you have a primary, actually it is a metal halide, even less than a primary. So this is metal halide. Here you have a tertiary halide. You see? What did we say earlier? SN2 reaction is the reaction what Williamson Ether Synthesis uses. So a tertiary halide, if you remember, in SN2 reaction, they are not a good substrates. SN2 reaction happens very rapidly when you have a primary alkyl halide and a nucleophile. So between this tertiary halide and a metal halide, which is not very crowded, which is very small, and it's even less than a primary, this reaction is much more favored. But here, this is a tertiary halide. So rather than undergoing actually an SN2 reaction, this is preferably does SN1. SN1 goes through a carbocation formation. If you have a carbocation, it could also lead to an SN1 and E1 competition. So it doesn't give you a clean product. So this leads to not SN2, because Williamson Ether Synthesis needs an SN2 substrates, meaning that a primary, maximum a secondary halide with a good nucleophile. So rather than this act as a nucleophile, and this portion should act as a halide. But here with the reverse, for example, if we make this a nucleophile and make this a halide, that reaction is not a good reaction, because this is not a good substrate for with a nucleophile to do the ether synthesis, because it has a competition of SN1, E1, elimination as well. It can eliminate from here because it goes through a carbocation. So these are SN1 and E1 kind of reactions. So it doesn't give a clean product. So this is not recommended, not a recommended combination. So in tests, you could face different kind of situations where you have to make sure the right combination for the Williamson ether synthesis. So this is the right combination where the metal portion is acting as a alkyl halide X. You could just use, for example, in a real example, you could use metal bromide plus OCH, the tertiary butoxide to make CH3O, CH3, CH3, CH3. So this is a good reaction for Williamson ether synthesis. So this is a Williamson ether synthesis. These are the combinations. You see, the ether is the same, but you are faced with choosing which combination you want to make so that you can react. This is a clean SN2 reaction. So Williamson ether synthesis is good when you have a good SN2 reaction counterparts. But here you have SN1, E1 possibilities as well. So this is not good for Williamson ether synthesis. So if you are asked to choose whether this is the right way or this one, or if you are asked to design, give two counterparts for this ether synthesis, you should give this counterpart, not this one's. Okay, so this is one small detail, which is very important detail in the Williamson ether synthesis. We'll continue now more on this with some examples of ether synthesis. Okay. From what I already described to you, we have to choose the appropriate alkyl halide and the appropriate alkoxide to make an ether from using the Williamson ether synthesis method. So here I have one question. I just want to explain more practical way of synthesizing ethers. So you have here a cyclohexane hydroxyl ethyl ether, which is this. So how do we synthesize this ether? So I'll go deeper in this. So if we are trying to do the Williamson ether synthesis, do I use this alkoxide or, meaning that this as an X alkyl halide and OCH2 CH3. Based on our discussion, your alkyl halide, here it is secondary. I think we are not using this because I can have the same ether, which is this ether, O, CH2, CH3. I can use the alkoxide to be here and the alkyl halide that. So the counterparts would be O minus plus CH2, CH3, X. So this is a good reaction design, right? So based on Williamson ether synthesis, that is a good counterpart because I can find ethyl bromide or ethyl chloride and reacted it with this cyclohexane alkoxide. One important thing, usually the alkoxides are not readily available. You can find, this is very important, you can't find alkoxides just in a bottle. They come as, for example, as alcohol. So that's, now I'm introducing a new concept for most alkoxides. For example, if you want to generate an alkoxide of this type, what you need to do is you start from the alcohol first, before you even do that reaction, to just generate this. These are generated in situ. That means in one part, in the reaction itself. We usually use sodium hydride. It's a very strong base that can pull off that hydrogen, because you don't need that hydrogen for the alkoxide. So the most commonly used base is sodium hydroxide. Sodium hydroxide. No, sodium hydride, sorry. This is sodium hydride. Sodium hydride. That pulls off the hydrogen to make a hydrogen gas and the alkoxide. So the alkoxide would be that in situ generated. Okay, you have a sodium plus hydrogen gas will come out. So the alkoxide is generated to make this. So as I said, alkoxides do not come just from a bottle. They have to be converted first while you are doing the reaction. For example, if we want an ethoxide, we start from ethanol plus sodium hydride, we get ethoxide, like that. So always the ethoxides are, if you are not readily available and somebody gives you the alcohol, you just react it with sodium hydride. It is a very strong base and you can generate that. So now let's go back to this ethoxide and also this oxide and that alkyl halide. So in the reaction, if the question comes, if somebody gives you this alcohol, and for example, if you are given an alcohol, OH, plus a bromoethane, CH2CH3, which represents that. Now first, usually when we do reactions, we do step 1 is removal of the hydrogen to form the alkoxide. So these are done in one part, meaning that in the same reaction vessel you add first sodium hydride, step 2 you add this. So if this was given like that, first step would be, let me just rewrite it, first step sodium hydride, second step you add the alkyl bromide, which is BrCH2, it could be a chloro as well, CH3. What is the product now? The product is exactly what you need at the end of the day. We synthesized this. So step 1, removal of, because you have to always form alkoxides. Alkoxides are always generated from the respective alcohol. So once the alcohol is, the proton is snatched and hydrogen gas is formed, you add your alkyl halide, the electrophile, we call it electrophile. Now you have the ether. So this is a good Williamson ether synthesis. Ether synthesis. Here, this portion of my lecture represents that how you generate alkoxide and how you then add the electrophile or your alkyl halide, and also a concept of how to choose two counterparts in the ether. Always focus on, for a good productive ether synthesis, in Williamson ether synthesis, you should always focus on the alkyl halide. You don't want the alkyl halide to be sterically crowded. You want to make it a primary, maximum a secondary. Otherwise, that counterpart would not be good. So in this is secondary, but in this, the alkyl halide is primary. So that's why I chose that reaction combination. But further, since you'll not always be given alkoxide in a bottle, it doesn't come, it's very reactive, you can't have alkoxide, very reactive nucleophile in a reagent bottle. You would be given a very stable alcohol. So you have to in situ generate the alkoxide. That's why you do two steps here, two-step reaction. First, alkoxide is generated. In step 2, I add the alkyl halide. Then I make the ether, the final product. So next, we'll see how also we synthesize epoxides. Now, in this series, we have seen how alcohols are synthesized. Alcohols are synthesized from a primary or secondary alkyl halide and hydroxide, sodium hydroxide, or potassium hydroxide. Ethers, in contrary, are synthesized from an alkoxide and a primary alkyl halide. And the general named reaction for ether synthesis is the one which is generated or discovered by Williamson. These are the most common way of synthesizing ethers is using a Williamson ether synthesis. So you could be asked in a mechanism or in a reaction, in a test that devise a Williamson ether synthesis, and what is Williamson ether synthesis? You could give an example. So we'll continue now. Next part of my video would be how to synthesize epoxides. So our chapter focuses on alcohols, ethers, and epoxides. Hence, I will also give you some ideas how epoxides are generated. So next, we'll continue on epoxide synthesis.